All right, again, AP Chem peeps, we're going to take a look at problem number 6. So, a buffer solution is prepared that contains zero point 0.5 molar NH3 and zero point 0.2 molar NH4Cl. For ammonia, oh, that's the NH3. Ammonia is NH3. The pKb is 4.75. Oh man, pKb. Okay, so the thing about this problem is that we're going to focus on this stuff. Learn how to write an ionic net ionic equation for an amine or in this case it's ammonia, but use pKa and pKb, pH of a buffer solution, and know when to use the Henderson-Hasselbalch equation and use Kw of all sorts, all that kind of stuff. So I'll kind of show you how to run through this problem, but we're going to stick with kind of our whole process. And we want to write a balanced net ionic equation to begin with. We know that we're starting off with, well, this thing, oh goodness, they have pKb, so we're probably dealing with a base. And then they have NH4Cl. But when I look at these things, it's like NH3, NH4, they look very similar. So I'm probably dealing with a conjugate. And when I write this out, I'm going to start with that NH3. And there's no OH, and is it going to give up an H? No, when you see NH3, this is a common base. And what it does is it reacts with water. So our water, it's a liquid, and this is our aqueous thing. And because they say it's a pKb, we're going to use it as a base. And that means that it takes on an H plus. It absorbs H plus. So we end up with NH4 plus aqueous. And that means that that H plus, it came from the water. So we have OH minus. Because it produces OH minus, that makes the NH3 the base, all that kind of stuff. But this is aqueous. So here's my base. That means that this was my acid in this problem. And this is my conjugate acid. And this is my conjugate base. Okay. So just kind of quick things to run through. But here's my balanced chemical equation. There's no ions that are spectators except for the Cl. I left the Cl out because when we look at Cl, Cl goes along with HCl. That's a strong acid. It completely dissociates. Because it completely dissociates and Cl is just here, we're not going to worry about HCl. And we can leave this out. And then this is what we got. And so now when I'm trying to figure out the pH of this, it's like, oh gosh, what do I got? Well, I have 0.50 molar NH3. And I have 0.20 molar NH4. And so now we get to the point of like, what do we do from here? Well, if we go back to that kind of scheme of how we work through problems, we wrote out our balanced net ionic equation. With stoichiometry, we don't have a weak acid reacting with a strong acid or base or anything like that. We don't do stoichiometry here. But we do have a weak acid base and its conjugate, and we can use an ice table. It's useful to have things in molar because then when we use Ka, Kb, all that kind of stuff, that's when we can, that stuff needs to be in molarity. So we're going to set up an ice table. And here we go. Because this is our initial values. And we want to figure out, to determine the pH, what the value of these things are at equilibrium. because if I can figure out the concentration of OH minus, then I can probably figure out the concentration of H plus at equilibrium too. So I'm going to do that. The H2O, I don't have to worry anything about H2O. But I know that I'm starting off with 0 concentration of OH minus. There's nothing in here that indicates what my concentration of OH minus is. My change, I'm going to end up shifting it over this way because there's no OH minus. It's going to shift this way and produce some OH minus. So I know that this is going to lose X or minus X. This is going to change by plus X. This is going to change by plus X. And they're all 1-to-1 ratio, or kind of like the coefficients are 1. So it's just minus X plus X plus X. So down here I get 0.50 minus X. This becomes X. This becomes X at my equilibrium. And now that I have those, I want to use it in my K value. And they tell me PKB. Oh, nuts. They tell me PKB. Oh, but I need KB. Remember, PKB is equal to the negative log of KB. So in order to get KB, I need to take 10 to the negative PKB. So it's 10 to the negative. They told me it was 4.75. And if I do that, I end up with 1.78 times 10 to the negative fifth. So here's my PKB, but my KB. My KB though, it's equal to, I can use KB because this has OH in that equation. Awesome. I want to check and make sure that it shows up that way, because KB, you have to have OH here. Otherwise, if it's H plus, you have to use Ka. So KB, it's equal to concentration of, I got NH4 plus, and concentration of OH minus, because it's products over reactants. Yep, concentration of NH3. And they're all coefficients of 1, so these are all to the first order. Great, and now I can put in my values that at equilibrium, I have X for that, X for that, and 0.50 minus X. But when I see plus X, minus X in this K value, I can kind of guess when I multiply this over here, that's going to get ugly because I'm going to have a square and I'm going to end up dealing with a quadratic. I don't want that. And so many times you can cross out that X only here because this is less than times 10 to the negative fourth. It will work. And now I can solve out for my X. I can multiply this by 0.5 over to that side, and I'll end up with and then I take the square root. 0.000444 is equal to X. But it's kind of like, now what do I do with that? Remember we went in search for X because we were looking for the concentration of OH? That is my concentration of OH at equilibrium. From there, I can figure out, because I know concentration of OH, I can figure out POH. It's equal to negative log times the concentration of OH minus, which equals negative log of 0.1234444. Sorry, it's getting messy. Equals. If I do that, my POH will come out to be 4.35. But that's my POH. I want pH. And so pH and pOH is equal to, if I add them together, I should get 14. If I know this is 4.35, I could subtract it from 14 and I get my pH is equal to 9.65. And that's awesome. And that's a long way of doing that. And there is a short way of doing it. I'm going to show you that right now. It still deals with kind of like how we set this up, but it's also recognizing that here I have my base and here I have my conjugate. That's what I'm starting with. If I have a base and a conjugate acid of it, or an acid and a conjugate base, kind of goes back and forth, I have a buffer solution. Nice. And if I have a buffer solution, I can actually simplify this. To solve for pH, I can use the Henderson-Hasselbalch equation. It's equal to pKa plus the log of your base over your acid. And so, a couple things here that we gotta just take care of. This is very specific because this is pKa, not pKb, but kind of from our equations and what works really well is that many things that are on your reference sheet can kind of work together. So like many times when we say like pH and pOH equals 14, it works the same way with pKa's and pKb's. 14, or those two things will add up to 14. So pKa plus pKb. That's cool. And so I'm going to use that in order to solve this out. And so use this equation, pH equals pKa plus pKb, or log concentration of A minus over AHA. Okay. But I need pKa, so pKa plus pKb equals 14. And this pKb we said was 4.75. If I wanted to solve for the pKa, I subtract that from 14, I get 9.25. That's cool. I can put that over here. Plus the log of the concentration of the A minus. This A minus is the conjugate base, or you can just think of it as a base, because HA, that's our acid. And so when I was originally talking about these, remember NH3? NH3 was actually the base. And so our concentration of that is 0.50 molar over the concentration of the acid. And it was the NH4 that acted as the acid, or the conjugate acid. It's the acid part. So we need to use that, even though they say A minus and HA, and this was NH4 plus, that doesn't matter so much. It's that this is the base part, this is the acid part, and this is what we got. So 0.20 molar for that piece. When I put this on my calculator, I need to do this first, 0.50 divided by 0.20, do the logarithm plus 9.25, and when I do that, I get for my pH, comes out to be 9.65, and it's the exact same answer that we got last time. So, two ways to solve it out, but if you recognize that this is a buffer, we're not adding a strong acid or a strong base to it, we can use Henderson-Hasselbalch equation because we're dealing with a buffer. And so we'll see in our next problem that we can also use this equation to shorten some things up, but we will need to do a couple other things with it too. All right, so see you there.